14.3 is on partial derivatives. So first let's review what we mean by a derivative in single variable. This would have been done in Calc 1. Defining f prime, or the derivative of f with respect to x. So the definition is pertaining to essentially a secant line. So if you have some function like this, okay, some curve, then the first thing you look at are secant lines. So you consider these lines that go like this and intersect the curve in 2 points. So it intersects here and, of course, here. And then you can get closer to the value you are approaching. So in this case, it's x. So if you get closer, you might end up with this line. And so the derivative is defined to be, well, the slope of the secant line is the change in the y values divided by the change in the x values. So as you take a limit, as h approaches 0, you end up getting this x plus a little bit getting closer and closer to x. And then you get the slope of the tangent line. So the slope of the tangent line is the limit as h approaches 0. Or you can define it like this: f of x minus f of a as x approaches a as the slope. So that's how you would have seen it in single variable. And the geometric interpretation of slope is also, or of the partial derivatives, is very similar. Okay, so we haven't even talked about that yet. So the partial derivatives we want to define next, and has a similar notation. We'll first just look at the mechanics of it, and then we will look at kind of the meaning behind it. The geometric interpretation will probably be the next video. Okay, so this is how the partial derivative is defined. So basically what you have to do is one derivative at a time. So it's still a derivative, but you treat one of the variables in your function of two variables as the one that's varying, and that's what you take the derivative of. And then you, on the other partial, you take the derivative of the other variable. So if I define this, it's f and the subscript x. That's the partial of the function f, or the partial of f, with respect to x of xy is equal to. So you can't say prime because you don't know what the variable is. And so that's defined to be the limit as h approaches 0 of f of x plus h, just like above, and then it's just comma y, minus f of xy all over h. And so that terminology is, zoom in a little bit, is, you would say, the first partial of f with respect to x is how you state it. And you can see that the limit definition is very similar. It's just that these all have comma y's in them, comma y. Everything else is the same. Then the next one, as you might expect, partial of f with respect to y of xy is equal to the limit of f of x, comma, y plus h minus f of xy all over h as h approaches 0. And that's the same, everything's the same except just you put y in there, of course. First partial of f with respect to y. Let's look at some notation of how we interpret that. Okay, so notation. So if you have z equal to f of xy, or z is a function of x and y, or f is a function of x and y. Excuse me, these are allergies. Then what you have is this notation, the same as above. Partial fx of xy is equal to, and then we use this symbol. Looks like a D, but it means partial. So you say partial, and you would say of xy. It's kind of the longer version. And then you say with respect to x. So when you're looking at these partials, that's pretty close. Okay, you don't cross it. It's not a D, right? So it's not like that. Like you start above and then you kind of curve it like that. And the symbol comes from the D, but it's just done a little differently. It's really not a letter that I know of anyway. It's just a symbol. It means partial. Excuse me. Okay. Or you can write that like this. You can say partial with respect to x. And you can put of xy in there like that. You can say a z instead, like y prime. Well, in this case, you say z and then you put a subscript of x. Or you could put z in there for the partial z, and then you say with respect to x, like that. And then same for y. I'm sure you could guess what this all looks like. Partial f with respect to y. It's partial f of xy. Then you have to state what variable you're taking the derivative with respect to. So that's y partial with respect to y of xy, z sub y, or just partial z respect to y. All right. Let's look at what you do. So this is the mechanics of how you take the partial. So we don't say derivative anymore. We actually say partial, unless it's just a single variable, which this isn't. So if you have a function of more than one variable, then we say partial. Let's look at this example. It's like, so what do you do when you do a partial? So let f of x equal x cubed y squared minus 2x squared y plus 3x. Then let's look at partial of f with respect to x. Okay, so what you do when you do this derivative is you look at the original function. You see your x is here, here, and here. When you're going through this, you're going to treat y like a constant. Y is just a constant. And then, of course, no y here. So when you go through it, it's just like this y is like a pi or e or 5. And you just haven't multiplied yet. So that's what you do. So this becomes 3x squared y squared. And then minus, so it's just x, so that'll be a 4xy, and then just plus 3. Okay, and then partial f with respect to y, same idea. You hold or treat x like a constant. And so now it's with respect to y, so this is 2x cubed y, and then minus that, and so derivative of y is just 1, so it's 2x squared. Now, what would this be? So what did I just say? Treat x like a constant. So that whole derivative will be just what? Exactly. It'll be 0. That derivative is 0 because there's x is a constant. Okay, so that's what you do. You've got to treat or keep. So you hold or treat x or y like a constant. And then take the derivative with the other variable. So this will be x and then this will be y. So you treat, excuse me, let's just leave it like that. We're fine. So it depends on what you're doing. All right, so next one, let's look at this question. Next example. So find partial of w with respect to y. If w equals xy squared e to the xy. Okay, now in this case, it's like having this as your f of xy and this as your g of xy. So if you have a product of those two functions, what must you use? Got to use a product rule. So you got to apply the product rule to that one when you do the partials. So it's with respect to y. So this x, you got to think of that as like a 4. It's like a 4y there, or 4xy squared there. I mean, it just tags along like a constant. All right, so always consider, so x, always think of that, right, in your mind. X is a constant. Okay, so let's do that. I'll throw in some other notation. Partial w with respect to y, partial w with respect to y. Okay, so now derivative of the first is 2xy e to the xy plus the first, which is xy squared, times the derivative of e to the xy, which is, chain rule, e to the xy times the derivative of the top, the function inside. The function inside is xy. We are treating x like a constant, so it's just derivative of y, which is 1, so you're left with just x. Okay, so go through that again if that didn't resonate with you. So you get 2xy e to the xy, and then you'll just write that as plus x squared y squared e to the xy. Okay, let's look at higher order partials. So higher order partials. So this is like first derivative, second derivative, third derivative, but now we're doing partials of those. First partial, second partial, and then we'll talk about mixed partials. So the notation looks like this. So if I say partial with respect to x twice, partial of f with respect to x. Okay, it might look like that. So z is equal to f of xy. We'll just keep that notation. Then basically what that means is partial, this is the same notation as the d notation, partial squared f with respect to x squared, or you could write partial xx like that. So that's the second partial of f with respect to x. And then similarly, partial respect to y, partial f respect to y. That's the same idea. So it's partial squared f respect to y squared, partial yy. That's the second partial of f with respect to y. Okay, let's talk about mixed part, and then you could keep going like that. Keep taking higher order partials. Mixed partials, a little different, a little interesting. So these are mixed partials. Oops, I didn't underline very well, did it? There we go. Okay, so now what if we want to change the order? So here we have something like partial with respect to y of partial f with respect to x. So that's partial squared f, and then it's y, then x. So it's kind of inside out. So partial xy is how you would say that. So this is the first thing you do, and then this. That's what this means. First, this is inside, and then the y. So this is basically means x, then y. So it's the mixed partial. I mean, you got to say each case. Then we can go the other way. So partial respect to x, partial f respect to y. Notation's looking weird there. Partial squared f respect to x respect to y. So it's partial yx. And you could go in any order. Like you could, let me give you, for example, you could say partial x, y, x, x, y, and just keep going like that. I mean, if it's a polynomial, obviously you're going to get to 0, but if you have cosines and sines or e, then it just keeps on going. So that this one would be first x, then y, then x again and again, and then y. Okay, so let's look at an example doing a mixed partial. I think I used the same one as above. Yeah, same one as above. So check this out. Actually, we'll just copy it because it's right there. Okay, so find partial fx, xx, partial fyy, partial fxy, and then partial fyx. So let's do each one of those, and we'll just do them instead of writing them down. So we already did partial fx, and we can leave off the xy if you want. That's fine. So that is 3x squared y squared minus 4xy plus 3. And then we already had partial fy above, so it's 2x cubed y minus 2x squared. Okay, so now let's do partial fxx. So you do the first one again with respect to x. So now you get 6xy squared minus 4y, and then plus 0. And then partial fyy, that'll be just the 2x cubed because the y is just that 1, and then what? Plus 0, right? So this is 0 because this is a constant. So constant gives you just that 0. Okay, then let's do xy. I'll just come over here. So this is partial x then y. So we're going to do the then y part. So the then y part gives us 6x squared y minus 4x, right? So this is this with respect to y. You get the 6x squared y minus, and then this is 1, so, or this is 1, I'm sorry, 4y. 4x, I'm sorry, 4x. And then that's a constant. And then now let's do partial f y then x. Okay, so do x now. And so you get 6x squared y and then minus 4x. So it's 6x squared y minus 4x. All right, do you notice anything interesting here? I'm sure you do. Okay, so you look at this, and you look at this, they're the same. Is that a coincidence? Does that just because it's a special function? So is that a special thing or not? What do you think? So coincidence or not? Not a coincidence. That happens all the time if you have continuous partials. So there's a theorem that states there's like a bunch of ways to define it and all that, but basically the way it's stated is continuous mixed partials are equal for any order. So that's the way I like to think of it. So continuous mixed partials are equal. And that is any order. So if you did partial x, y, y, z, as long as you do a partial of x, a partial of z, and two partials of y, they're all the same. So it's the same as partial x, y, z, y, partial y, y, zx, right, etc. So as long as you do two of these and then one of each of whatever it may be, they are the same. They're equal partials. That's going to come in very critically when we look at some theorems in the future. That's defined, of course, much more carefully in later stuff where you got to define f to be continuous, and then their mixed partials are continuous, and then of course they're equal. Okay. So I think that'll be it. We've got to do geometric interpretation in this section. And then definition of differentiability, another important concept. And yeah, that's it. Okay, so a couple more things to do. We'll do that in another video.